3.2, conditional probability and the multiplication rule. So with conditional probabilities, what we're going to talk about first. We're going to talk about how do we calculate probabilities with these multiple events going on. So based on what we have, we're going to calculate them as such. So with conditional probability, this is the probability of event occurring given that another event has already occurred. So this is going to be our keyword. That one word in a probability problem is going to tell us that we can't use a total and we have to use the conditions that we already know. And this is how it's written on your formula sheet. And then we're going to look at that word given and circle it and find out what do we do. So let's look at our first problem. The table shows the results of a survey in 970 U.S. adults, and they were asked, and adults were asked, have they ever ridden as a passenger in a self-driving vehicle. Find the probability that the adult is 18 to 64 years old, given an adult has ridden as a passenger in a self-driving vehicle. I gotta reword that. That looks weird. All right. So given, there's our word. So whatever comes after that, that's going to be our total for our denominator. So we're going to X out that total, and we're going to use this as our denominator. So I'm going to look at the characteristics, that's what I'm looking for, characteristics that the person has ridden in a vehicle before, a self-driving vehicle before. I use event E because that's what they use a lot. You can use A, B, C, D. It doesn't matter what the letter is. I just use E a lot because I use E a lot for event. So 225 is going to be my denominator. So that means I can't use this because I know that they've ridden in a self-driving vehicle before, self-driven vehicle. So I can't use this. I can't use this because it has no in it. So this plus this equals this. This plus this equals this. So that means this total has no in it, and I can't use the no's. So I can't use the totals. So I can only pick from ages 18 to 64 or 65 plus. Gotta pick one of these two. So I'm going to look before the word given, and that's the one number I'm going to use. So I'm going to use 1864. I'm going to do that one more time. So given, I circle it because that tells me I can't use my total. I underline it, and I look for that characteristic. The adult has ridden as a passenger, so that's a yes. So this is the only column I can use. And then I'm going to look before the word given to see which of the two options I have. And I'm going to use the 202. We put that in the calculator. What do you get? 0.898. Let me switch this around. So find a probability that an adult is 65 years or older, given the adult has not ridden as a passenger in a vehicle. So given, I highlighted this, they have not ridden, so I'm only using this column this time. So I can use columns, I can use rows, whatever they ask you to do, that's what you use. So this time, what is my denominator going to be? Good, because it's after that word given. So my denominator is going to be 745. I always look at that first, because I can figure out my denominator. I get to choose which of those numbers that makes up that number I'm going to use. So it's going to be the 549 or the 196. So 65 years or older, I'm going to use the 196. So this was the denominator. Could use 970 because of that given. And then I had to choose between 549 and 196. And this was the number that corresponded with the 65 years or older. Okay? So talk about independent events. The occurrence of one event, one of the events does not affect the probability of the occurrence of the other event. Meaning, we're talking about one event occurring and it has nothing to do with the other. Events that are not independent are dependent. I mean, I need to know what happened first so I can adjust later. I need to know what happened first so I can adjust later. Let's look at some examples of this. Selecting a king from a standard deck of 52 playing cards, not replacing it, and then selecting a queen. So I have 52 cards. I'm going to take a king out. That's event A. I'm not going to put it back, but I do want to go back and get another queen. So did the deck change, or did it stay the same? It changed, which means it's dependent. Not putting the king back. Made the card total. I'll put that. Made the card total change to 51 to choose from. Just think about that. We didn't put the king back, so that means I did not have 52 cards to choose from when I went to go get that second card. I only had 51. Okay? Tossing a coin and getting ahead, then rolling a 6-sided die, and I'm taking a 6. So I'm trying to toss a coin to get ahead, and then roll it out to get a 6. Does my tossing the coin affect the die? No, it does not. I didn't have to go back and pick it up or do it again or leave it there and it affected everything. Those are two different processes. So these are independent. Two separate objects. So I didn't pull from the same bag. I didn't pull from the same bag of Skittles. I didn't pull from the same deck of cards. Things like that. That's dependent means I only have one, and I'm doing something twice, or I'm affecting it twice. Alright, and 3, driving over 85 miles per hour, then getting in a car accident. This is the one I have to fight my risk takers with. These are dependent. I know my speeders would think differently, but these are dependent. Speed was a factor in the accident. It was. I know you don't think so, but it was. Alright, let's talk about the math that goes with this. Alright, the multiplication rule. The probability that two events A and B will occur in sequence is the probability of A and B occurring. So this is our key word. And means to multiply. It also means we're doing one thing, we're stopping, and then we're doing another. And we stop to make sure we decide if our second fraction is being affected. So we're doing more than one thing after the other. So I'm going to pick a card, I'm going to pick another card, I'm going to pick another card, and I stop in between those. So for this first one, when they are dependent, I'm going to multiply my first probability times the second probability, noting that something different is going to happen because it's affected. I'm pulling from the same bag, pulling from the same card deck, something. They have something in common. Because it has an A and an A, so something is in common. For independent, the rule can just be simplified to multiplication, one after the other. And we could do this a number of times. So we can pick 3 cards, one card and the card and another card. So we'll have a PC next. Alright, so let's look at this. 2 cards are selected without replacing the first card from setting their cards. The probability of selecting a king and then selecting a queen. Selecting a king and then a queen. So I think I may have put a card deck on your formula sheet. If I did it and you need one, you can either Google or ask me to send you one and I'll send you one. I think I might have one. Hopefully I do. Hold on. Okay, I found in your book under section 3.1, under types of probabilities, they do have this here. So if you need it, so I'm going to refer to it real quick. So my probability of selecting a king and then a queen. So let's look at what we have. So kings, we have 4. Queens, we have 4 of those as well. And this is a standard 52 card deck. Now I've lost my pen. Hold on. Yeah, found it. Okay, here we go. Alright, so 2 cards are selected without replacing the first card. So that means I'm not going to put my king back. I'm not going to put my king back. So when I pick my king, so with probability, let me just kind of explain this. Probability is what's going to happen, or what's the probability before you do what you're doing. So when I pick my king, I have 4 kings to choose from out of the 52 cards. So before I pick, that's my probability. 4 out of the 52 cards, I have 4 kings. But my queen, I have 4 of them. We looked at those 4 of them. But I don't have 52 anymore because I didn't put that king back. So now I have 51. So I took one of the kings away. And I don't have all 52 cards. I only have 51 to choose from. This number changed because this problem was a dependent problem. I didn't put the first card back. So now I'm going to pick a king and then a queen. So that means I want to multiply these 2 together. You do not have to know how to multiply or add for these problems. So let's get the calculator. I don't think it matters again about parentheses, but that's just something I like to do. So 0.006. 0.006. Remember, this is very unusual. This is below 0.05. That's below 0.05. So that is unusual. It's actually very unusual because it's a low decimal. Okay? So let's look at the flip side, or another part of this. 2 cards are selected. Without replacing the first card from a standard deck of 52 cards, find the probability of selecting a king and then selecting a king. So I'm picking the same card again. I'm not putting that first one back. So the first one, remember, we look at it before we pick. I have 4 kings out of the 52 cards. But then I'm going back to get another king. I have to think about how many kings do I have left now that I'm not putting that other one back. So if I took the king, I didn't put it back, I don't have all 4 kings anymore. I have 3 kings to choose from. So this is before the first pick. Then I pick on the space. Before I pick my second king, what are my probabilities? What do I have as a possibility? What are my possible outcomes? So I'm down 1 card, and that specific card is a king, so that did affect my top and my bottom number this time. Because I went back to get another king. I already took 1 king, didn't put it back, and I'm going to get another one. So that's a probability. So before I pick my king, that's the probability we're looking at. Before I pick my king. So go back to my probability of E and E. Put up the calculator. There we go. Let's do one more kind of like that so we can see about the dependent, independent, and then see how this actually works out. So a coin is tossed and a die is rolled. So these are 2 different objects. I know this is independent, so I don't have to worry about my denominators changing or my numerators changing. Find the probability of tossing a head and rolling those 6. So a head on a 2-sided die, from a 2-sided coin. Coins only have 2 sides. The probability of me picking the head is 1. When I'm rolling a die, I only have a 6. I only have 1 6 on a 6-sided die. I only have 1 6 on a 6-sided die. So that and tells me I'm doing this and then this. You can multiply and get the fraction if you want to, but remember, we want decimals, so there's no need for you to kind of show off and know that you're not multiplying, add fractions. Just do the calculator. Not unless you just want to show off for yourself. Hey, have at it. But we just want that decimal value. Alright, the next one. So here we're actually making up our fractions. In the next multiplication rule, they give us the probability, and we're doing something over and over again, which means we're working that fundamental counting principle. So for ACL reconstructive surgery, the probability that the surgery is successful is 0.95. So they give us our fraction as a actual number, a decimal value. Find a probability that 3 ACL surgeries are successful. 3 ACL surgeries are successful. So that means the first surgery is successful. The second surgery is successful. The third surgery is successful. I think I might put this in parentheses because of all the little dots. Yeah, we do that. So fundamental counting principle, first, second, and third. So let me show you what this is and what this isn't in the calculator. This is not this. This is not 3 times 0.95. Plus, we can't have that as an answer. Why? Why can't we have that? Think about it. That's over 1. That's more than 1. So it can't be a possibility. What it is, really, 0.95 to the third power. But I would just do the fundamental counting principle. just so that you won't, mess up anything or make a mistake with this shortcut. So I would do this every single time. I know it's quicker, but just keep it consistent. All 3 surgeries are successful. That's 0.857. Find the probability that none of the 3 ACL surgeries are successful. Think about that. If we have success on the first surgery, it's 0.95. What is no success? What is no success? Good. So no success for the first, no success for the second, no success for the third. How do we get this 0.05? 1 minus 0.95. What a complement. So this is success. This is not success. This is success. That's not success. Good. So let's talk about that answer. 0.05 times 0.05 times 0.05. Our answer is not 1.25. Remember, we cannot have an answer over 1. This e-4 means we're dealing with a really small number. So let's convert this. 1.25 e-4. This is not an answer because it's not in standard form, standard number form. This is in exponential form. So what we're going to do, we're going to take the number that we see, and we're going to move our decimal left 4 because it's negative. 1, 2, 3, 4. So 1, 2, 3, 4. So add 3 zeros. So this is what it looks like. We normally round to 3 decimal places, but I don't want to leave it like this because this means no possibility. But we actually do have a possibility. So we want to round to the next or nearest non-zero number. Now there is a problem in your homework. I believe they prefer you to keep it like this. You'll know when you get to it, it'll say, hey, your answer's wrong. Even though it's supposed to be this, it'll say your answer's wrong, so just keep it as 0.000. But if you have a possibility, you want to round to the next non-zero number. So 2 makes that 1 stay the same. I don't want to just have that. I want to have this number showing that it's a really, really small probability, but it's possible. Really, really small probability, but it's possible. So normally we round to 3 decimal places, but we want to do 4 so we can show that there is an answer. It's just really, really small. Okay, we'll talk about that if you need to in class, or if you need to email me. I can talk about that a little further. Next one, you're going to have to rely on Miss Gibbs for right now. Just rely on Miss Gibbs for right now. So find the probability that at least one of the 3 ACL surgeries is successful. At least one is the complement of none successful. At least one is a complement of none successful. So whatever you get for that last answer, you're just going to take the complement of it. So at least one is 1 minus none. Pause and make sure you do that. At least one is 1 minus none. So you put that in the calculator, you get this. And we'll talk about this a little bit later in 4.1 or 4.2. It introduces it here. It just uses it as a complement for right now. But we'll talk about why it is what it is a little later. Let's do one more of those. Let's do one more. Just make sure you're good. Let's do one more. This is out of your book as well. Number 25 is the section 3.2. Still. So in a sample of 1,500 adults, U.S. citizens, 270 said that Barack Obama was the best president in U.S. history. 2 adults, U.S. citizens, are selected at random. So we're going to select 1 adult and then select another adult. So find the probability that both U.S. citizens say that Barack Obama was the best president in U.S. history. So we're going back to the fraction for this one. It didn't give us a decimal, so we're going back to the fraction. So both adults say Barack Obama was the best president. So we have 2 adults. The probability of picking the first adult is 270 because 270 said that he was the best president over 1,500. So we're going to pick one, and then we're going back to pick another. We can't put that person back in because, you know, when you take a survey, normally you don't put them back. So we're not going to put that person back. So because we're not going to put the person back, and this person also believes that Barack Obama was the best president. That's from the same pile. That's from the same group of people. So find the probability that both adult U.S. citizens believe Barack Obama was the best president. When you put this in your calculator, what do you get? Okay, good. By the probability that neither adult U.S. citizens say that Barack Obama was the best president in U.S. history. So now we're looking at the opposite. They think they're the best. Now we're picking someone who does not think he's the best. So what's that top number going to be now? What's that top number? We still have 1,500 adults. Think about that top number. Good. 1,230. So we got 1,500 people. 270 believes that he's a good president. That means 1,230 believe he's not the best president. Not good, but the best president. So if this adult does not think he's the best president, the next one's the same. So we're going for the same pile again. So what's our fraction? Good. Okay, so 0.672. Good. So here's that at least one now. Find the probability that at least one of the 2 adults say that Barack Obama was the best president. We always take 1 minus that, none. That's 0.328. 328. Good. D. Let's talk about D. Which of the events are considered unusual and why? Which of the events are considered unusual? So this one. This one is below 0.05. So both U.S. citizens saying both U.S. citizens say Obama, I'm going to shorthand this, was the best president. event, or A. We put A as well. And Y, the probability was less than, not last, less than 0.05. That's less than 0.05, so it's like 3.2 cents. This is like 67 cents. And this is, this is 3 cents, 67 cents, 32 cents. So remember, anything less than a nickel, that's how I remember it. I know, money, can't go wrong. Anything less than a nickel is unusual. Anything a nickel or less, actually, is unusual.